Okay, good afternoon, Professor, everyone. Today I'm going to present the paper Enhancing Mobile App to Use Sensor Hub Without Program Effort. And I'm John, and here's the outline. So let's start with the motivation. So nowadays, many applications heavily rely on the continuous sensing and monitoring for tasks. For example, the step counting and fault detection, all those kind of applications require continuously fetch the sensor data on the phone. So what's the problem with this scenario? This kind of scheme will drain battery quickly because they prevent the main processor from sleeping. This is because the main processor will need to, as I mentioned before, will need to keep fetching the data from the sensor. So that will take a lot of power. So the current solution is that, as the figure shows here, we embedded a separate microcontroller in the sensor hub. So this microcontroller will operate continuously to retrieve the data from the sensors like a gyroscope, accelerometer, or GPS. So in this case, the whole CPU can sleep to save the power. That sounds really good, right? But the problem of this approach is that the microcontroller is very difficult to program because the APIs provided by the microcontroller are application specific. And also, they are not cross-platform. Probably some APIs work only on the HTC phones, while others only work on the Samsung phones. So that's causes a big trouble for developers. So this paper proposed another solution called MobileHub. So the main idea of this MobileHub is that how do we just buffer sensor data as long as possible in order to keep the main CPU idle? So in order to achieve this objective, there are three questions to answer. First of all, how long can we buffer the data? So in the paper, they will use the machine learning algorithm to learn the pattern from the sensor. And the second thing is that how to know what sensor value wake up the CPU. This is particularly important because we don't want to buffer the data that will wake up the CPU. Otherwise, we will possibly alter the behavior of the original application. So in the paper, they use the technique called dynamic taint tracking. And the last question is that how can application on the stock market make use of our system? So this can be simply achieved by application binary rewriting. And we will look into all three solutions later. So here comes the system architecture. So in MobileHub, it involves 4-step pipeline. And we will examine each stage closely. The first one is the user trace. The user trace is defined as a series of data values that collect from the sensor. It's pretty straightforward. And this user trace can come from, of course, can be collected from the sensors. And it can also be uploaded by the developers. Yeah, because later on we are going to use the machine learning algorithm to train our system. So we need to upload the training data to our MobileHub. So we need this functionality. Okay, so here comes the first step, the dynamic taint tracking. Why do we need dynamic taint tracking? So here's an example. Consider a fault detection application. And those are the sensor values that we retrieve from the, let's say, accelerometers. And this application will simply trigger an alarm when the sensor value exceeds some predefined value, let's say 65 here. So the main issue here is that, okay, now the cell phone received a trigger or the alarm. And we observe that there are 5 possible values that trigger this alarm. But how do we know exactly which value triggers this alarm? So that's why we need this dynamic taint tracking. So basically, the dynamic tracking is to track how program input at the source affect the program output at the sink. So in the previous example is that what sensor value triggers the alarm. So here introduce.
So just curious, I mean, sometimes
yes.
It may not just be the value that you are seeing, it may be some complicated function of that which triggers, right?
Yes.
Can you talk about that?
Yeah, of course. So here comes two types of data flow. I will introduce this. So when the sensor data from the accelerometer and GPS comes into the applications, so the application will process or make some calculation or as you mentioned, that will go into some functions, and eventually it will produce some side effect called, or send, for example, send a notification to the user, or will trigger an alert, or your smart home will vibrate. Yeah, so as the data flow in the applications, we can easily categorize them into two different classes. The one is explicit flow, and the second one is implicit flow. So the explicit flow is the information that is passed from the right-hand side to the left-hand side of an assignment. So here's the example. The sensor value is directly assigned to the variable x. So this is the explicit flow. And of course, the x is going to the function, and return value is assigned to the y. So of course, this is also explicit data flow. How about the implicit data flow? It's referred to the information that is associated with the control flow, but without any direct assignment operation. Take this code segment, for example. Here, the sensor value is assigned to variable x. Obviously, this is an explicit flow, but later on, this variable is not appears in an if-else statement. This is a control flow block, and it affects the variable step. So once this variable is higher than some predefined threshold, it will cause the step to increase. In this case, x is actually not directly assigned to the variable step, but actually it will cause the step to increase once it exceeds some threshold. So in this case, we call it implicit data flow. So after we have all those two flows, let's see how we know which sensor data triggers the application side effect. So for example, we have data coming in from the accelerometer, let's say 10. And for each data value, we will assign a unique Taint tag to that, let's say T1. So after it goes to the application, after the application did some processing, and the value eventually becomes 0.9, but the Taint tag is still the same, but no alert happens. So we will give an invalid mark to this sensor value. And secondly, another data comes in, and it becomes, say, 1.5, and no alert happens, so it's still invalid. And now another sensor value, 100, comes in, and it becomes 55. Now a lot happens, so we will mark this sensor value as active. And another comes in, a lot happens, we mark it as active. So by doing so, we can know, yeah, because the sensor value may possibly change in the application, but this Taint tag will never change. So in this way, we can know what sensor value actually trigger the application side effect. Okay, after finish the first step, we go into...
So do they have like a one-to-one mapping between value and which value? So like, for example, what if it was something like, only when I see a third 0.9 in a row will I output an alert. Okay, so first 0.9 gave nothing, second 0.9 gave no alert, but third 0.9 did. So how do they handle that situation? Will you talk about it?
Yeah, I think they just simply report that all the sensor values that trigger the application side effect. So they will not distinguish the same values. And okay, now here comes to another step. So now we want to learn the range of sensor data. Yeah.
Actually, regarding the professor's previous question,
yes.
If I remember what I read correctly,
yes.
What they do is they don't filter on what data triggers effects. What they filter is what data definitely does not trigger.
Yeah, exactly. I'm going to talk about this. Okay. So in this part, the mobile will learn the range of sensor data that do not trigger the application side effect. Yeah, because the data value triggers the application side effect may be...
So if a data value ever triggers, it's marked as a trigger, but if it never triggers, that's...
Yes. So yeah, because Yeah, because those data values that trigger the application side effect, they possibly are outliers or noises. So it's safe to distinguish them from those values that not triggering the application side effect. So basically, they use conventional machine learning to do this. It includes 4 steps. So the first one is we obtain all. Remember that we mark each sensor value as inactive and active. So now we want to convert this Taint log into the training data. So basically, what they did is we will do the clustering. We will group those sensor value, inactive sensor value, which are close enough to active sensor value to be active. So that because this one is very probably it's an outlier, or because in our application we may use some techniques like smoothing or like average over a certain period of time to determine whether we trigger the application side effect or not. So we want to smooth out that kind of effect. So we use the clustering technique to do so. So here's an example. For in this period, there is an active sensor value here. So we will mark this whole period as active. And for this period, there's no there are only inactive sensor values, so the whole period is inactive. So eventually, we can come up with smoothing data. So that will be the training data of our machine learning algorithm. So the next step is to select the training features. So they can be either the maximum value, minimum value, the range, or the mean, whatever. So in the paper, they perform the leave one out cross validation to select useful feature for them. And finally, they want to find out what machine learning algorithms are best for their experiment. So here are 5 possible machine learning algorithms, and we can see that the random forest and the naive Bayes achieve the lowest error and the lowest delay compared to other 3 algorithms. But in the paper, we don't use the random forest because it requires lots of memory. So at last, we use the naive Bayes in the approach. So the final stage is after we have the trained classifier, so now we are able to make the prediction based on the sensor input. So this trained classifier will predict whether we can safely buffer the sensor data in the sensor hub or not. And again, because we don't want our classifier to be biased toward those outliers and noises, so we will use a finite state machine here to again smooth the final predictions. So basically, it involves 3 states. So if we are in the active period, we will constantly predict that this is active sensor data. Otherwise, we will predict it's an inactive sensor data. So the third step is we actually implement the classifier onto our platform. So here's the test platform they are using. This is the prototype board which runs an animal microcontroller on it, and we will implement the classifier that we trained in the previous step into the firmware of this prototype board, and we will connect it with our smartphone. So the last step is to rewrite the existing application to make them leverage our sensor hub. So basically, we will first of all implement user-level sensor hub services. These services provide a unified interface for all the applications. So once the application is going to retrieve the data from the sensor hub, so basically it will not call the APIs to the sensor hub. It will use the Android binder, which is an inter-process communication mechanism built in the Android to communicate with the sensor hub service first. And the sensor hub services will communicate with the sensor hub on behalf of those applications. So after the sensor hub retrieves the data value from the sensor, it will return to the applications. So basically, but how do we let the application to make the function call to our sensor hub services? It's very simple. In Android, we can modify the binary code easily. So we just need to replace the function call in the existing application with the new function call to our sensor hub service, and that's it. So here's the evaluation, and we evaluate our system on 20 applications with lots of different kinds of sensors. So here we can see that in terms of energy, it results in a 33% of energy improvement on average. And because we know now...
So just a sec. So in this case, they are comparing for the unmodified application, it was still using their external sensors, or was it using the sensors on board?
External.
In both cases,
yes. Okay, so because we now, sometimes we need to buffer the data in the sensor hub, so we may introduce some delays. So they also evaluate this effect. And according to the experiment result, we can see that our approach only delayed the application update 1.87 of the time. And meanwhile, the application side effect remained the same. So that is a pretty good result. So here are some related work mentioned in the paper. Like we can either do the software optimization, like better sensor algorithms, hardware optimization, like we can embed those buffer onto the sensor. And of course, heterogeneous architecture like the one we are using now, like we use a separate processor on the sensor hub, and lots of related works. So here's the strengths. First of all, it will automatically write application binary to leverage the MobileHub. So remember that we don't need to. It does not require the program source code because we directly modify the binary code after the compilation. So this process can be done automatically. So no additional programming effort are required. So that's a pretty good improvement. And the second advantage is that this user-level sensor hub services provide an unified interface for all kinds of applications. So even various applications may need different kind of sensor, but it doesn't matter as long as we can use this. Well, as long as we can run this sensor hub service on our platform, and we can use this sensor hub service to retrieve data from the sensor hub. Yeah, and another thing is that it successfully utilized the static analysis to identify the potential implicit flow in the control blocks. This step is in dynamic Taint tracking. So the detail is in the paper. So here I'll just briefly mention it. So because usually in the application there are tons of control blocks. So it's impossible for developers to analyze them one by one. So in the paper, they propose a very efficient way to do the static analysis to identify those potential implicit flow beforehand so that they can avoid exhaustive search through every control block in the application. And on the other hand, it's only add a few lines of code, so it's pretty efficient. And another thing is the data smoothing technique in the learning stage really help to get rid of data outliers, noises, because we all know that those sensor values are really prone to be affected by the environment. So we definitely need this approach to make our system not biased toward those noises. So the techniques we use is the clustering and the finite state machine. And there are, of course, some limitations. The first of all, it did not take external input into account. For example, some application might need interact with user, like the user may hit the button on the smartphone, or the user may tap on the screen. So some application may need that information. So in the current approach, we didn't take that inference into account.
Not sure I understand. So why is this an issue?
Okay. Let me go back to. Yeah, because currently our system only takes the sensor value as input. So if the user like interact with the application on the phone, our system will not detect that behavior, so that we will miss it.
Because why would you not detect it? Because when I'm tapping, right?
Yes.
You're saying so the application is woken up only when there is data, or application? Why would the application miss the user tap? I guess.
Yeah, because it's not a hardware limitation. It's because currently our sensor hub only retrieve the sensor data from only retrieve data values from the sensor.
Correct.
It won't, yeah.
So other data like the tap on the screen is still directly being sent by Android to the application,
Yes.
right?
Yes.
So the application still wake up, right? So why is that an issue?
Yeah, I mean, because let me take a look. Here's it. Yeah, because when we are doing the dynamic Taint tracking, we only take sensor data into account, like the sensor values from accelerometer, GPS.
Yeah, but that is only for buffering, right? So
yes.
So the issue basically is that instead of the application getting woken up every time a sample is coming, now it's being woken up after a few samples have been collected, right? Okay. But the user tapping the application is a totally separate thing, right? So
yes.
Why would that be affected?
Because I think, I think it's not a limitation, but they just didn't take that into consideration.
So is that limitation something coming from you or from the paper?
They slightly mentioned that probably it's future work or something. Yeah. So.
Go ahead.
What they mentioned is that they are taking the raw. I mean, they are looking for the event of interest. Sometimes that is just the raw sensor data.
Yes.
Sometimes it's like the sensor data and manipulated with some kind of action.
Yes.
And that's the
yes.
Event of interest. So what they're saying that their application is not taking that into account. They're only taking the raw sensor data, and if that's the event of interest, that they can classify.
Right.
If there is some external parameter that is affecting the event of interest, then that's not.
Right. Thanks.
You want to read?
No, she said okay. In better words than I would have used.
Okay. So another limitation is that as long as a training process is involved into a system, sometimes very difficult to fine-tune the parameters in that system, because basically all machine learning algorithms are not deterministic. So it's highly dependent on the input training data. So if the input training data is not good, probably we may end up with a bad classifier. So this, okay. So, and another thing here is that in the paper, they only measure the total energy consumption for the entire system. So the individual component, or say the power consumption of the prototype board is not measured in the paper. So I think in the paper, we will not be able to estimate how much energy overhead caused by the.
But that's probably
paper.
not an important thing, because clearly their MobileHub is a prototype, right?
Yes.
I guess what they're saying is, imagine if this were to be built into the phone.
Yeah.
Right?
Yeah. So that's why I think that it's better to measure the energy for individual component, because currently they are using a prototype board. I think it's easier to measure the power consumption of that prototype board than the one. Yes.
Okay.
And the last thing is that because now we will buffer the sensor data in the sensor hub, so sometimes it may introduce a small delay, probably up to 1 second. But for some applications that require an instantaneous response time, that delay would not be tolerable, like, for example, a heart attack detector. So that may seriously alter the side effect of the application. So here's some future work.
It also raises an interesting question that for sensors which are meant to detect these kind of rare events, how do they train it?
Yeah, that is also a problem. Yeah. Yes, yeah, because as I mentioned, if we are lack of the input training data, so basically the machine learning algorithm won't work.
So did they talk about like how long did they have to train for?
No, they didn't mention that. Yes. First of all, of course, we can extend the current platform to the current system to other platforms. For example, tablet, wearables, and indeed other operating systems, iOS, Windows Phone. And of course, as we gather more and more data from the sensor, we can dynamically retrain the algorithm so that it can produce a more accurate prediction. And also, there are other advanced machine learning algorithms available so that we probably in the future can also try all those algorithms. And also, we can use adaptive buffering policy during runtime because the more aggressive we buffer the sensor data, the higher energy saving we have. So I think it's probably feasible to make the system as a power management method so that according to the different system load, we can adjust our buffering policy so that we can achieve probably an overall better energy saving. And of course, the last point is that we can support the user input and other type of event in the future. So because nowadays, our applications are more and more diversified and powerful, so we may definitely consider all those factors. I think that's it.